lecture is organized by the Kolkata chapter of Indian National Academy of Engineering and the Academy of Science and Technology in association with the University. And we are very fortunate to have Dr. Debashish here. Of this institute, is a global leader in sustainable technologies and energy transitions. The university of senior leadership at Tata. And many of Lionstead ventures venture investment in high-tech startups focused on smart manufacturing, decarbonization, and responsible innovation. For translating science into scalable solutions, he holds over 78 patents and has received 15 honors, including fellowship of the Royal Academy of Engineering, Indian National Academy of Engineering, and the Academy of Science and Technology. The National Metallurgist Award. His accomplishments span establishing a carbon capture unit at Tata Steel, scientific conversion of coal tar waste in EV battery, and carbon fiber, and creating the first RP-based structure. He has instituted international R&D collaborations and complex and advanced materials business, achieving 50 million in revenue. Today, engineers in lecture, we really cannot find someone better than Dr. Bhattacharjee. Before we invite our speaker today to the podium, we also read through the message that President of FNAE Kolkata chapter has sent because of this. He couldn't be here, so we have had a message. And I'd like to announce the lecture 2025 plans organized by the Royal Academy of Science and Technology and the Indian National Engineering Sector in association with Jadavpur University. This is the challenge of critical materials, energy transition, and company industries. And it will be delivered by Dr. Debashish followed by both activities. With his distinguished career as managing partner of Lionstead Ventures, professor of practice at Madras, and former vice president of technology and R&D at Tata Steel, is uniquely in position to further engineers on this important topic. Due to that reason, I am unable to be present in person. I am confident that this lecture will be a source of great inspiration for all participants and online. This is the program of every practice and institutional wishes to follow. Thank you. Thank you for the introduction. Thank you for inviting me to deliver the Engineers Day lecture. Sometimes we don't know how luck would take its course. And this, my invitation coming my way was serendipitous. So a mistake of mine. I had to go to an office in Jadavpur
few months, I think a month back, in the electrical engineering department, and I landed up at the Provinci's office. And after some cups of tea and coffee and idle banter, which I think your Provici didn't just have time for, but he was very kind to me. So I think all in all, I think I had to repay in some way. So I said yes to the request of delivering this lecture. And it's my pleasure to come back to my alma mater, where, which actually created the platform on which uh, my small career took off. I always say, and I say to my friends and family, that two institutions have contributed the most to me. One is the work, and the second is Cambridge. They made me who I am. And the other institutes took the result. So I'm delighted to be here, humbled to be here, and it's always a pleasure to come back to Jadavpur for whatever reason, for idle banter, for making mistakes in office, in finding offices, or even to give lectures. I'm also very pleasantly surprised and happy to see so many students. When I was a student, I know how I felt when I had to go and sit in a lecture which has very strong sounding words and boring sounding names. So I'm again very thankful to the students for being here today, and I'll try my best to not make it too boring, and hopefully we'll go back learn more. And also, I have learned a lot in the process of making this lecture. Try not to repeat lectures, so I make lectures. Each of my lectures are fresh. The topic is of relevance today, because as we see around the world, geopolitics is being dictated by the choice of material. You would wonder why. If you hark back a few months, you'll see that one of the presidents of a large country, which wants a war to stop, signed a pact with one of the warring countries and said, now we have a solution. And the pact was on the basis of critical minerals that are available in the planet. Just one example. We've seen in many other fora that civilization is based on materials. You had Stone Age, you had Copper Age, you had Iron Age, and now we have Silicon Age. And we will have some other age going forward. Of course, mechanical engineering plays a part. But plays a large part. I have to go home also after this, right? So I cannot have drum faces with my audience now. Let's say it's the material engineers and the materials that form the basis, and the rest of the world comes and takes those materials and makes things, equipment, structures, which are then of use to civilization. The wheel first came using stone, but of course now we have we have moved forward. We had bronze wheels, we had iron wheels, and now of course we have rubber tires on wheels, even aluminium wheels. So the world progresses on the platform of materials. And as we stand today in this world, by the way, how long do I have? I have no intention of finishing in the next 5 minutes. 1 hour. So students, will you bear me for 1 hour? 55 minutes? I didn't see any nodding of heads. So 55 minutes is also not right. So let's come to a... Oh, more than that. Okay. I was not getting any response on 55 minutes. Okay, so there is no limit. As soon as you feel bored, you let me know. He says, as the world transforms, it transforms on the basis of materials. And as we stand today, we see major things happening in the world, which is transforming the world as we speak. And many times we don't see transformation when we are in a transformation. We hardly notice the transformation of telephone on the desk to a handset, which was not a smartphone, and then to a smartphone, and soon there'll be no smartphones. Happened in the last 25 years. We are seeing a transformation that is happening on energy. And everything, the world runs, they say the world runs on money. But the world runs on energy. Whether you want to run automobiles, planes, ships, whether you want to manufacture materials, whether you want to mine materials, whether you want to construct bridges, you need energy. Whether you want to attend classes, you need energy. To go home from class, you need energy. It's energy that runs the world. So, if we look at the world from the energy perspective, it'll be one window, one lens of seeing how the world is transforming and how underlying materials are gaining importance, losing importance, and having a huge impact on us and on politics and policy. So energy consumption is increasing every year, day by day. So 602 was the exajoules of energy consumption in 2022. I was trying hard to find out what it was in 2025, 2024. They're still trying to collect all the data for 2024. But the last available data, which was published in 2024, was of 2023, is 620 exajoules. So it has increased by whatever percent, small percent, but there's a gradual increase in energy. And it has happened continuously over the years, except for the years in which world stood still and everyone stayed at home. The COVID period, there was a dip in energy consumption. So this energy has to come from somewhere. Our energy comes from food. But food is essentially carbon, oxygen, and hydrogen. So we burn carbon, and the carbon comes out as CO2. So most of this energy also is carbon. The world has been using this energy, the 620 exajoules of energy, mostly 80% from carbonaceous fuels, coal, petroleum, and gas. If you add the percentages, you'll get to over 80%. Lately, you're getting to new renewable energies, solar, and wind, and nuclear, etc. But they form cumulatively less than 20% of the world. Now, why is this important? It is important because of the carbon that we are burning to run the world. And this energy of 620 is running the entire world. It's running even the data centers that are hosting your AI tools. ChatGPT has a significant contribution to the 620 exajoules. So it's not only the steel factories, it's not only the ships and planes, it's also the data centers that are running AI programs, large. And this burning of carbon gives CO2. And that CO2 increases the temperature of a. I've not put those slides. But I think you will know all of this, right? Do you know how much increase in temperature we can tolerate till the end of this century compared to 1750, start of the industrial era? But how much can the world tolerate increase in temperature? No? 1.5 degrees. if the world temperature goes up by 1.5 degrees by the end of this century, that's 2100, compared to what it was in 1750, we are in danger of losing water. We are in danger of temperatures going so high that many of the current animals will become extinct. If we go to 2 degrees centigrade, it's only a 0.5. You could say it's a measurement error. But if it goes to 2, humans may not exist. If it goes to 3, definitely humans will not. The rate at which temperature is increasing today is already having an effect. You can see the intensity of natural disasters increasing across the world. Many other things are happening. And as the clock ticks, it is ticking at a rate at which it is very clear that we have already gone past the 1.5 degrees centigrade increase. Irretrievably, we will definitely fail that mark. So we have to do things to arrest the world before it reaches the 2 degree centigrade mark. And the only way you can do that is by reducing this energy consumption or reducing the carbon-based energy consumption. And now imagine that's 80% of our energy consumption. So that really, other than hydro and nuclear, have to rapidly increase over the next decade to have an effect. And of course, there are many efforts that are on the way. This energy consumption is also not uniform. It varies widely across the world. So US, for example, is one of the biggest energy consumers per capita. US is 34,000, India is 7.7, 10 times. Per capita energy consumption of US is 10 times higher than. The Middle East countries are even higher than US. But some of them consume coal, like India. Some of them consume gas. Some of them consume oil. So it's quite a mixed picture. So if you just address one, you may not have a global solution. You need to address multiple energy sources to get a global solution. Just look at oil. The world today consumes about 101 million barrels per day. A barrel of oil, 1 million barrels, 101 million barrels per day, of which nearly 18-19% is consumed by US. India is number 3 in that list. So although India per capita is low, the number of capita is high. So it's US, China, and India. So in terms of our carbon dioxide footprint, it's proportional to the amount of oil we are burning. It's proportional to the amount of coal we are burning. And this carbon dioxide is going to come back and hit us and our children, you and your children. So it's not a myth, it's a reality, and it needs to be tackled. So that was the oil picture. So this is the coal picture, global coal consumption. Today, the world consumes 9 billion tons of coal per year. And as you see the graph, it is increasing. And it is increasing driven by a few countries. Many countries have given up coal simply because they don't have it. They are using gas instead, they are using petrol instead. But all are equally bad. So this is an indication of how things are changing. These are some of the countries which have taken positive steps based on regulations to bring down fossil fuel consumption. Fossil fuel being oil, coal, natural gas. and increase renewable energy consumption. So these nations, although their per capita consumption is high, they have already started showing a decline in fossil fuel consumption. Coal and oil, which are the darker shades, the grayer shades are going down. The brighter shades are growing up, which is good news. But that is also a result of their geography, what is available to them, the techno-economics, and also the political mileage that they get. India cannot simply say no to coal. There's huge amount of that energy source available at low cost, and there's also a human cost to that. India and China are one of the biggest users of coal, and that curve is going up. In fact, if you look at entire Southeast Asia, coal and oil consumption are going up. So while some of the developed countries are showing a lowering trend in fossil fuel consumption, Southeast Asia is balancing that in a way by continuing to increase fossil fuel consumption. And that's because they need more energy, and this is the most easily available energy source. But that is not to say that these countries are keeping quiet. That's what. So these countries are also not keeping quiet. But this is, before I move on to say what these countries are doing in terms of energy, there's a glimpse on India's crude oil consumption. Out of the 101 million barrels per day, India consumes roughly 5%, as I showed before. India doesn't produce much oil. So therefore, it will import a large part of that consumption. And India's import gradually increases. 12 and is now 243 in terms of million tons of oil. It costs India today about 12 lakh crore rupees of foreign exchange. That's a huge outflow of money. There is an interesting thing you can notice from this graph, from this data, and you'll understand why certain countries are very angry with it. You see, India's oil consumption has increased, but its cost has decreased. That's because it has found a source which is low in cost, which some others don't like. Right? But it clearly shows it's a couple of lakhs of crores of benefit that India gets for itself. But the point still is it's still 12 lakh crore of outflow from the country for this energy material. And it is not a surprise that India as a nation is working on renewables. You see much more solar panels on fields, at airports, even on rooftops today than even a couple of years back. India's renewable energy growth has been phenomenal, absolutely phenomenal. So today, the installed capacity of renewable is about 190 installed capacity. That's not what it produces. The red line is the non-renewable. And in terms of installed capacity, the numbers are slightly different because of different dates at which these numbers were taken. India is number 4 in the world in renewable energy installation. China is number one. So although you see India and China increasing its coal consumption, they are parallelly increasing their renewable energy installation as well. And the renewable energy growth is more than the growth through fossil fuel energy. So as a result, progressively, the contribution of renewable energy in India's energy scenario is a net increase. And India's renewable energy is mainly driven by solar. You hardly see any wind turbines here. I mean, in Europe, you see a lot of wind turbines all over the place, both offshore and onshore. But India has a lot of garam hawa and many places of power. But India's hawa doesn't give much power. So India is not amenable to wind energy in this geography. So solar is the most prevalent. Now here comes material. So that's where my talk gets from global and national energy scenario to a material platform scenario. The fundamental of solar energy is the solar module. And the active material is the solar cell, silicon-based solar cell. Yeah, that is clear to everyone. There is a silicon solar cell. And the way the silicon solar cell is manufactured is it starts from sand, quartz, SiO2, which is reduced with carbon. So it has carbon footprint into silicon or metallurgical grade silicon, which is about 99% pure. And then it goes through multiple chemical processes to get to 99.7999s or 11 nines or 13 nines purity. And then it is directionally solidified and then sliced into cells, either single single grain solar cells or multiple grain solar cells. I mean, how difficult can this be? This is metallurgical plus chemical process. Can't be that difficult. This is the country-wise distribution of the ability to manufacture solar cells, not the module. Can you see the name of the country there? So 92% of solar cells in the world are manufactured in one country. It's actually manufactured in one province of that country. And there is a reason why so. I'm not going to get into the reason. Now, what does this mean? It means that when India wants to increase its renewable energy in the grid and has to use solar cells for that renewable energy, it is almost 100% dependent on just one country to supply the solar cell. And can you imagine if that country just switches off the tap, just puts a barrier, tariff or non-tariff, and we are very familiar with tariff barriers now. Just a tap is switched off. India's growth in energy, in green energy, will come to a stop. Such is the power of a material. Now let's look at the rest of the solar. This is the module. This is the solar cells together with two glass panels and a back and a etc. Those are not very difficult to make, to assemble. So many Indian companies buy the solar cells and assemble to make the modules. And it is with these modules that India has become number 4 or number 3 in the world in renewable energy. So a lot of Indian companies are now making modules. That's what we see from India sitting in India. Globally, still, more than 80% of these modules are made in China. So just imagine the power that one country has on one source of renewable energy. They just switch off and the world comes to a halt. I'll stay a bit and give an example of magnesium. Magnesium is a light metal. This can be used in medical, can be used in automotive. The way to make magnesium is through fission process, which is a reduction process. This country, they found a way to subsidize this process to such an extent that prices of magnesium drop in the world. That's a good news, the price of any metal drops. But it is not so for the entrepreneur or in another country. Because that entrepreneur has to put money in to develop a new technology, which will make magnesium. But if that magnesium doesn't give money because the prices have dropped, you will have no extra cash to put into development. So all worldwide initiatives for magnesium, new routes to magnesium development stop. So 90% of magnesium today comes from one country. 90% of silicon for the solar cell comes from one country. How material plays a critical role in business, in global dominance, and therefore politics. So as a nation, our renewable energy policies, renewable energy initiatives are heavily dependent on import. So we talked about electric energy. The other driver for changing the energy source is automotive. Transferring from oil-based IC engine to battery, green electricity-based battery and motor-driven power grids. And no matter what you say, people, think EV will come, it will not come, Teslas are too expensive. But the trend globally is that EV consumption, EV buying is increasing. And it's increasing huge. It's also increasing in India. And typical of India, it has found its own solution to make automotive electric and green. World looks at four-wheelers, looks at light trucks, looks at transportation within the city and between cities. India's EV revolution has come through two-wheelers and three-wheelers. Four-wheelers is very small. So those large numbers that you see in hundreds of thousands are essentially two-wheelers and three-wheelers. But the transition is very clear. The Ola scooters are all electric scooters. The Apple scooters are all electric scooters. And people will buy these electric mobility. So as I said, powertrain is shifting from oil-based ICE to battery and motors. Now let's look at, again, the influence of material on this energy that makes you roll. This is just a picture of battery materials. The common lithium batteries, the lithium nickel cobalt and lithium LMN batteries, there's LNC batteries. Some nickel cobalt, some nickel cobalt, nickel cobalt, in various proportions and lithium. This is all cathode material. As you know, battery has cathode in it. This is all cathode material. None. None of these materials are made in India. 100% imported. There's a new trend in battery chemistry away from lithium, nickel, cobalt, manganese, which is the LFP batteries, the lithium iron phosphorus batteries. We have iron. We have phosphorus. So maybe here, India can jump the queue and be a leader. So we saw that the lithium batteries, or everything has to be imported. So we don't make batteries because since everything has to be imported, might as well import the battery. Why import individual elements? In LFP, the world has already moved forward. This is a new battery chemistry. The top 10 companies that make lithium iron phosphate batteries are all Chinese. BYD, which is a car company, is number 2 in the world in making this battery. They move fast. Let's look at the anode material. These are all graphite, these are all cathode materials. Let's look at anode material. Anode essentially is graphite. You know graphite, right? Pencil that has some other gang material, but it's essentially graphite. Some pure form of graphite goes into battery anode. This is from an annual report of a company in India. By 2030, they say if India makes some of these batteries, India will need about 230 or 280,000 tons of battery grade graphite. India doesn't make close to that. Some countries are putting in plants in anticipation of that. And that plant itself has got 50% of the demand by 2030. We will not even match our demand in the next 6 years with all the planned installed capacity. We will continue to, we today import 100% here, and we will continue to import even graphite for the anode of the battery. And this is the scale of dominance. So you don't have to read everything. Just look at the colors in this graph. So this is the materials have to be mined. Lithium has to be mined, manganese has to be mined, nickel has to be mined, cobalt has to be mined, graphite also has to be mined. So mining dominance. So look at this one color. This one color doesn't have much mining dominance except in graphite. The next step is getting these materials into your country and start refining materials processing, and then going further downstream to cell components and then battery cells. Just one country has complete dominance on materials and that. They may not have the natural resource, but they need to know that they have the mines under their control, live in their country and have materials processing and subsequent assembly. So therefore, we have read in the newspapers recently that car companies are worried that they will have to stop their lines. They will have to stop their lines because some of these materials will be stopped by assembly. And that certain countries' name is not difficult to guess. If any one of the components, lithium or manganese or battery grade or graphite is stopped, Some electric vehicle companies will come to our. We don't have no battery. So India needs to leapfrog. India needs to find solution beyond what is currently available as technology. Current technology is perfect. So can we look for, this is an indicative slide. It's not a prescriptive. Can we look for other sources, algae to carbon? Can we look at non-carbon? Can we look at silicon-based anodes? And so on. If you don't look at it, be sure somebody has tried it. And if somebody has tried it, it is not commercial, means there is a flaw. Can you address that flaw? So there's one lady. So ladies and gentlemen, ladies and gentlemen, we are desperately trying to replace oil with other energy materials. But in terms of that 11 or 12 lakh crore rupees of outflow from the country, that is not stopped. Because we're replacing one energy material with an entire set of other energy materials which are all input. Let's look at another part of the power trade and see what India can do. So this is where we go to slightly different track. We have been seeing what India is not doing and India is already behind, fine, but what can India do? So this is an electric motor. Are electrical engineers here? Then I'll be a bit defensive. So essentially, this is an AC electric motor which goes into electric vehicles, not a BLDC. So essentially, it has a stator and a rotor. So it will have magnet and it will have stampings, electrical steel stampings. Now, these electric steel stampings, there was a company called GKW in Howrah a few decades back. That was my first place of work from campus. They used to make stamping. The Sankey electric stampings were made by them. These fans have motors which have electric sheet stampings. When motors need to be rotating at high speed, these stampings need to be thinner and thinner, and they need to be of chemistry that reduces loss. If these stampings are thick, then there is a resistance loss because of it. This is fundamental high school level understanding of Ohm's law. So you make these laminations as thin as possible. So as the motors need to go to higher and higher revolutions per minute, as the RPM goes up, the need to prevent loss of the motor. You need to make thickness as small as possible. These electric steel scales have to be brought to much thinner gauges than India's thinnest road for electric purposes is about 0.27 millimeter. Electric vehicles use motors that have sheaths of thickness 0.2 millimeter and below, or 0.22 millimeter. All those sheaths have to be improved. There are magnets. Permanent magnets. Permanent magnets are NDFEC, NDFEB, boron or cobalt, neodymium, and iron. So clearly, neodymium is a rare earth, has to be imported. Cobalt comes from the Congo, has to be imported. Iron, 67% is iron. That also needs to be imported. Somebody should ask why. Why does iron need to be imported? We have so many iron mines and iron companies, iron steel companies. The reason is this iron has to be very pure. 99.5% purity iron and above. That iron is made either through arco iron, by electrolysis and deposition, or by other chemical processes, not from the steel mills. India does not make a single ounce of this iron. So all that iron is imported. So again, just like battery, just like the silicon metal, we don't make magnets, we import magnets. The same point. Now here's a concept which is transformative, and it can make India self-reliant on magnets with its own materials that are available in India. Next 10 minutes, you have to bear me out. Listen to this story. To have these motors run at high speed and with high efficiency, low loss, you need to reduce thickness. India's steel mills do not have the capability to go below 0.27 millimeter. Putting a mill and then finding a market, etc., is a long run process. Let that happen. But think differently. Imagine you have powder, iron powder. Iron powder can be, you can spray dry it, or you can mill it, you can get to 50 microns very easily. That's significantly lower than your 0.27 millimeter that you get. Now you can say that will magnetic flux go through this powder? It will. If you have ever dismantled the motor, you have found that these laminates of steel, which are thick 0.27 and above in India today, are separated by a coating. Each sheet is separated by a coating. It is separated because had it not been separated, that would have all been one conductive mass. So the net thickness would have been this. So each is separated by a non-conductive coating, either a phosphate coating or a magnesium oxide coating. So you take powder particles of iron and you coat with the same coating, phosphate coating or a magnesium oxide coating. You then effectively reduce thickness from this powder to laminated coat or powder. Effective thickness comes down to 50 microns. And now you have a powder. You also have flexibility in form factor. You don't need to have a stack all well aligned. You can your motor design is fixed. Because it's a powder, you can simply compress it into any shape you want. In a shape that is determined and defined by the most efficient motor you can design for the purpose it's used. So this is it. These are powders which are coated, compressed. You will get into the stator rotor assembly. Now, usually these motors are called radial flux motors. Radial flux because the flux is coming out radially. And for radial flux motors, there is an engineering reason why they are radial flux. Because the stamping is easy. All these laminates can be just one shape and size. The holes can be aligned. So one stamping process creates thousands of these laminates. But a more efficient motor would be an axial flux motor, not a radial, but an axial flux. For an axial flux motor, the laminates are not horizontal, they are vertical. And because it's a round, you can imagine that these vertical laminates have to converge towards the center, right? So each laminate is of a different size compared to the previous. As you go closer to the center, they become smaller and smaller. How would you simply press and get a easy laminate out of it? Each is a different size. But if you had particles that are coated, you simply need to press that into shape. That's it. One pressing action and you have the entire coat. So you can make axial flux motors. If you have regular axial flux motor, one layer of steel stamping the other of iron powder, and if you go up in frequency, the axial flux motor shows lower and lower iron loss. A typical high frequency motor that goes into EV runs at about 8,000, 10,000 RPM. That is where ideal motor would be an axial flux. Powder metallurgy enables you to do that. Normal, traditional way of making electric motors don't allow you to do that unless you get to very thin sheets, which India doesn't make. But this powder, India can make. So you can get lighter motors for longer range. You can get space. This same iron powder, without the coating, can get into permanent magnets. The iron that you need to import today for permanent magnets, that iron you don't need to import. This iron powder gets into that space. I'm not going to explain to you the magnetic flux. And as I said before, if you're thinking of something new, be sure that somebody else has already thought about. So there is example in the world that people are using powders for motors. The Hoganas, which is a powder metallurgy company, is using their powder for motors, and JFE, which is a steel company, is using powder for motors. Way back, not in your childhood, but in our childhood, we used to have radios with valves. You switch on a radio, it needed some time to warm up and the valves to blow and the radio to start. That radio had a transformer for high frequency transformer to catch the frequencies of the radio waves. If you find such a set, open the transformer. The core of the transformer which conducts magnetic flux is a powder, not laminate. So people knew the use of powder even before for very high frequency. Just never, the dots were never joined to make that available for rotating motors. And now comes the last bit. In a permanent magnet, last bit of this story. I'm not letting you go through it. Permanent magnet, 67% is iron. This iron can fill that place. The remaining 33% is still imported. Neodymium and cobalt, boron. What do you do about that? You take another leap of faith and jump over traditional technology and say that we make a magnet, permanent magnet, without rare earth. Thermodynamically, it is possible to use nitrogen. It's all in the crystal structure and the orientation of the spins. Nitrogen plays the same role, but it has a very narrow stability rate. So the role of the material scientist, and I'm glad Vajda is here. The role of the material scientist is to find a way to make this narrow phase stable at reasonably high temperature. This is Fe16N2. Fe16N2 will give a permanent magnet of the same quality as NdFeB or NdFeC permanent magnets, without the need for imported rare earths, without the need for imported cobalt. I've been saying that this iron powder is local. Although I started by saying that purest iron powder has to be imported. So why am I saying this iron powder is local? Why am I gloating about it? The reason I'm saying this is because it's a new finding where one particular reject of a steel plant. Have you seen steel rolls? the streets, in the roads, that you big rolls of steel. Some are brown, rusty, and some are not so brown. Some are very shiny. Like steel that goes to make your car is not rusty, it is shiny. So to convert from that rusty steel, which is hot rolled steel, to a shiny steel that goes onto the car body, it needs to go through cold rolling. But when you do cold rolling, you have to ensure that the rust doesn't get rolled in. So you have to do pickling and take away the rust. That rust is very superficial and it's very fine. So when you filter the acid that has gone into the pickling process, you get a residue which is almost pure Fe2O3. The steel that gets into car bodies are almost pure iron, very low alloying contents. They're called interstitial free steels. So very low carbon, very low nitrogen, very low, because if you add alloying elements, they become strong and you can't form them. So they're almost pure. So if you take that rust, which is almost pure Fe2O3, and reduce it with either hydrogen or ammonia, not carbon, then you get almost pure iron, 99.5% and above. This, this is obtained as is from the pickling line, and this is as obtained that reduced by hydrogen or ammonia. So this material has been obtained from a reject of a steel plant. And the only processing step needed is a reduction by ammonia or hydrogen. No mining, no chemicals. So obviously this is green and this is cheap. And steel plants in India produce tons, thousands of tons of this. This can go and make the motor materials which are imported. This can go and make the magnet, 67% of permanent magnets that are imported. And if you can replace neodymium, 100% of permanent magnets can be made by this material. So this thought, this way of thinking, and by the way, this is not just thinking. This prototype exists. It is already patented. This way of thinking is needed by our country to find solutions for ourselves using our materials. Otherwise, forever we'll be dependent on some other country to supply us and be vulnerable to tariffs of multiple sorts. So all that we discuss are very critical to humanity. We started with humanity. Silicon, iron, neodymium, cobalt, nickel, very critical to energy and traction, rolling traction. So the government has gone ahead and identified 30 such minerals, which are critical from the perspective of energy, from the perspective of defense, aerospace, health, and electronics. And these critical minerals are dispersed all over the periodic table. Some are here, some are there, and we have already spoken about many of these. Some we have not spoken today. This is not meant to be a comprehensive lecture. And more of them are here. These are the lanthanides and actinides, the rare earth elements. So we need to find, we don't have large deposits of this. So therefore they're critical for us. So we need to find alternate ways to get access to this, to bypass these, and therefore we need new technologies. We need technologies that will make use of our low-grade ores. We have ores, but we have low-grade. So this is Sukinda. You know where Sukinda is? It's in Orissa. Anybody from Orissa? Nobody. Other than chromite mines, they have fantastic patha. The quality of goat meat in Sukinda is best in the world. So if you go there, please don't forget to taste it. They are local, free-range, banyan tree fed goats. Other than that, when they mine, they take out the soil and put it in the topsoil. It's called the overburden. That overburden has 1%, nearly 1% nickel and 0.1% cobalt. that makes it really lean. It's not very rich. But that's what we have as a nation. So we need to find a way to extract that nickel and cobalt and find a technology that does it for us. So, for example, people are thinking about making direct reduction and coming to nuggets, or electric arc furnace after some beneficiation. We come to cobalt nickel alloys. Now, cobalt nickel alloys can be used in defense, or you can use another process, subsequent process to separate cobalt and nickel, and you get the two metals separate. There is a cost to it, but there is also thrill of developing the technology for the nation, and it is possible. So this is a proposal that came from one of the jobs in the government. So you take batteries, spent batteries. So this is about recycling. Spent batteries have all the materials in them. All that we talked about that we can't get. Those have been given to us. So why can't we extract those elements from the spent batteries, from the spent magnets? That's a source, right? In fact, it is, if we look at the trend, by 2050, 50% of these elements are going to come from recycling and remaining 50% from Mother Earth. So we need to find a way of upscaling recycling technologies very fast. So this is other people sending raw materials to our country. Today what we do is we take this spent material, melt, take the gold out, there's a lot of gold in this. Take the gold out, melt, it becomes a black mass and send it abroad. And some other country does the final refining and get the material back. We should do the refining here. So there are many proposals like this with the spent batteries. It could be spent electronics, it could be spent magnets. Convert them into useful metals which can then be recycled back into batteries and back into magnets, etc. We should also look at new approaches. I talked about a new approach in iron powder. This is 5 kilometers below the ocean on the seabed. These are called polymetallic nodules. And I brought one for you to show you. Can I just see? You want to toss it around? This came from 5 kilometers below the sea. And India is now working on ways to mine, to extract this from the seabed. It is not easy. You can't send a person with a shovel to pick and put it in a wheelbarrow, bring it up. So you have to find a technology to bring it up from the seabed and the technology to extract the material, because this is not something you get on Earth. So the technology for extracting the metals from this sea nodule will be different from the existing technology that is used for other minerals. And of course, there is, we don't know what we don't know. Nearly 90% of India's land surface has not been surveyed for minerals. 90%. So when we say that we don't have that particular mineral, we are saying from the knowledge we get from 10% of the land. And we haven't surveyed because it is just difficult to survey. And over the years, we just haven't taken that initiative. Now there is a reason to expedite it. You can't send people with dipsticks all over India to go and do that survey. That's too slow. So we have to find new techniques such as airborne surveys. And these are now coming. There are startups which are proposing airborne surveys with different types of sensors on the gliders and on the planes and drones. And I think with the expertise that is available in any university, especially my alma mater, you could have materials working with sensor experts, working with people who can design structures and machines, come up with solutions for our indigenous material to serve the need of India's critical minerals. So in summary, we need a policy framework which the government is very fast, very alert, and has already put in place. It's funding for indigenous research and for local solutions. And again, I must say that what more government fund is available for this than private fund. Multiple ministries have floated calls for research proposals in critical minerals area and in energy. And of course, I suggest, this is who am I to suggest, but I take the, I'm making this assumption that I can suggest there's a need to relook at some of the course material. And we were just talking, you said hydrometallurgy should be brought back. The point is, I think it is definitely necessary in metallurgy to bring back process metallurgy strongly. The world today is looking at extraction from minerals, earth minerals, extraction from used objects, so urban mining. It's looking at different ways of sensing minerals in the ground. It is looking at ways to process material into useful objects. So I think I will leave Professor with this thought that maybe metallurgy courses can be looked at how to enhance. I know over the years process metallurgy has depleted across the world, but now is the time to build it up again. Similar need may happen in mechanical. I'm in no place to suggest for mechanical, and this whole domain is multidisciplinary. As you saw, we talked about motors, types of motors, we talked about structures, we talked about battery chemistry, we talked about materials. So in multiple domains, there's a need to relook at our undergraduate syllabus and therefore research afterwards to tailor ourselves and the next generation to work to have the necessary skill and knowledge to work in these areas for the nation. And of course, there's one aspect is the higher education, the other is skill development. The skill needed in electronics, skill needed in battery manufacture, skill needed in magnet manufacture. Since we haven't done those as a nation, are absent, that skill development needs to go hand in hand. With this, I come to the end of my talk. Thank you for the time. Thank you for bearing with me. And I will be able to do that. I'm happy the students were still awake. Yes, please. And the government of India, in some of the meetings that I said, they're fully aware of this. It has never been a priority. Now it is a priority. This is where we are, right? And therefore, if you look at the National Critical Minerals Policy document, they are talking about expediting exploration through multiple technologies, and they're looking for ideas and proposals for new technologies for rapid exploration. We never went out there seriously as a nation outside India to explore and procure. China has been doing that for the last 25 years. And therefore, they're in a position where they can, even if they don't have the resource, they have processing capability because they can take and bring. We don't take and bring from outside. We don't even take from, we don't know our country. So now scenario will change. So like many things, we are late starters. But once the focus is given, hopefully, no, not part of this talk. Correct. Correct. Yeah. Yes. Small. 0.5%. It is. There are many, what should I say? See, once you let somebody take a lead in a domain, and that somebody also has the ambition to continue to take the lead, it's difficult to catch. If you have a Usain Bolt, and you and I go and compete with Usain Bolt, it won't happen because we just don't have the legacy. We have not practiced. So, a 25-year, 30-year legacy of a country of, of, of single-minded strategy is difficult to beat if you're a newcomer. It will take us another 25, 30 years to come to that level. Assuming that country will still stand still. It will not. It will also run forward. Keep on running forward. Yeah, so you have to see this. Silicon. We're talking about silicon. Silicon, the game is after the seventh place of decimal. Not before seventh place of decimal. That doesn't count. So India's manufacturing is before seventh place of decimal. China goes from 0.7 place of decimal to ninth place of decimal. Some 11th place of decimal. It still can't go to 13th place of decimal. There are only two companies in the world that make 11 nines and 13 nines. China imports from that small amount. So you see, it is not easy technology. And anything after seventh place of decimal is proprietary knowledge and proprietary technology. That they will not share. So you either have a market strength, so you bring a joint venture, or a monetary strength, or some other offer which will give that person the carrot to come and set up something here. Now, today the carrot and the market and everything else is in one country. So the main enabler, main bottleneck for silicon manufacture up to the cell is electricity. It's humongously electricity. It's an electricity guzzler, the process. So if electricity is expensive, and our electricity get this part, even the cheapest parts in pockets of the SEZs, etc., where there are special rates. Electricity there is still 2 times the price of electricity in special areas in that country. So you can't beat that if electricity is your main cost factor. So it has to be seen holistically. You don't have the technology. You really don't have the technology. And you can't suddenly say that we will have the 9N, 11N technology today. It will not happen. Because the countries and the companies that have done it have done that over the last 30 years. And they have the trained manpower to do it. So it's a big issue to bring that technology. Unless you bring that technology, you will not play in the global market. You will only play in Indian market. But then how long can you prevent imports from coming? Better imports from coming at a lower price. So it doesn't eventually, when you do the scenario, it doesn't make commercial sense. So you'd only play in that small range which needs that 7N and lower silicon. So it's a small part of the market. So the solution is you jump that technology. You cannot be a follower. You have to jump. So the next, if you look, there's an NREL draft for solar. I'm sure you've seen that NREL. They update it every year. All technologies ever in the world that were in solar are plotted in the graph with year and efficiency in 2 axes. If you look at that, you'll see that some of the new technologies which have started lately and have now matured, such as on thin sheet, on flexible sheets, perovskites, for example. Perovskites are now coming of age. I think we may have still missed the boat on perovskite, but we can try. This is a good enough time to try to jump from silicon to perovskite, or to bolster the silicon with perovskite, to do a hybrid solar cell. But we're not thinking in that direction in a big way. We have to leapfrog. Only leapfrog can give us leadership. And I want to also leave you with another thought. Recently, I'll start somewhere else and I'll come back to the point. There are many areas in which India is behind. There was a strategic reason for being behind because we had many other obstacles to cross. So making our own planes was never our, as a nation, never our prerogative. We could buy from both. But now with the changed world scenario, we find that many things we have to do ourselves. That globalization has gone. It's all localization. So you have to be expert in almost everything. So we have to build our own planes. We don't have capability. We don't have the material. We don't make a single ounce of carbon fiber. We don't make titanium. The two fundamental structure materials for aeroplanes. Now, Government of India floats a call for proposals for what to do to make aeroplanes. I get a call from a management consultant saying, there is a call. Can I use your CV? What do you want to use my CV? I said, no, the call says that experts have to be there. And they have said, there are 9 areas in which experts have to be there, and one is materials. What is the role of that expert? No, there is no role of that expert. Then why do you keep my CV? No, that's needed. So if something happens, we'll call you. This is not how leadership is attained. Leadership is attained through technology, not through management consulting. And that we have to firmly remember. So if you go to this large country we are talking about, they have at least one, if not 2 universities in every material. So if you talk about carbon fiber, there are 2 universities dedicated to carbon fiber. It means they teach everything, but everything is oriented towards carbon fiber. Physics, ultimately oriented towards carbon fiber. Chemistry, materials, mechanical, everything is oriented towards carbon fiber. There are 2 universities oriented towards steel. So I was a visiting professor in one of that university in Beijing. It was earlier called Beijing Institute of Science and Technology. Sorry, it is now called Beijing Institute of Science and Technology, earlier called Lionstead Institute. They have 320 PhD students only working on steel-related projects, covering automation to process material, but steel-oriented. From that university, they are running experimental on-trial control software for Baosteel in Shanghai from Beijing University in Beijing. They are funded. Their funding is $1 billion a year. And it is not Tsinghua. It is not the top university. 320 PhD students in steel. Whole world doesn't have it. It is in one university. Exactly. There was a coal research lab, 70 stories building. They've just kept the top story free for future expansion. The scale, the ambition, scale, followed up with implementation at scale and technology. It is done through core technology. You cannot do these things and you cannot attain leadership in these areas without technology leadership, not management consultants. Sometimes our country forgets it. Yeah, exactly. Yes. Thank you. Oh, that's good. No, no, I know what you're saying. I said there's more garam hawa here when there is power, and there is less power where normal hawa is available. That's what I said. But yes, true. The every geography, it's available in internet. You can look at the quality of wind. So if no, it's not nothing to do with quality. It's just geography. The way the wind is channeled, the way the currents move, that's that. North Sea area, uh, west west coast of US are fantastic for wind power. So you see a lot of offshore in those areas. Indian offshore is good in South India, but not everywhere. And onshore is really good. You know, it's good. It's much easier to put solar than wind. And the panacea will be fusion, not fission. So, you know, so- yeah, it's positive to God. Of course, it's not. But you see, if you cost is always relative, and cost also is time dependent. So when the first electric vehicle battery came out, the cost was from today 70 times higher. So that cost decreases and also is relative to other technologies that are available. So the two I talked about, the one using lean ore, that also is very expensive when it finally comes to the metal. It's you work out the relative and in a time span.